heard about a couple issues with the lab so far. Has anybody run into anything that seems like it should be working, but it's not? That's a good way to say it. All right, the note that Monica sent out to everybody yesterday about correcting the quality of service, that's actually corrected in the file online now, so if you download it, it should be all set. All right, well, let's continue on talking about sensor architectures. And today what I'd like to get into is hyperspectral type systems, and then we're going to look at some issues about calibration and how you calibrate these sensors. All right, so. All right, so you're about ready. All right, so we looked at single band sensors, and we looked at sensors where we might collect a handful of bands. Okay, and the handful of bands we talked about using a prism or a dispersive grating or something to break up the white light into its spectral components. And this next step, going to what we call hyperspectral sensors, might seem, just a little bit more of the same. But I guess what I want to establish is usually what in the industry right now is accepted definitions for a multispectral and a hyperspectral system. All right, so it used to be that we used to say, well, multispectral systems had a couple bands, maybe 5, 6, 7. And then hyperspectral sensors have lots of bands, like 100 or 200. But now there's all kinds of sensors in between there, so we need all those sorts of things. So I guess a more formal definition is if we had a set of spectral response functions for the detectors on the different bands for the system. A multispectral system might have spectral response functions that might look something like this. All right, and they may spread, down from the visible, maybe out to the shortwave infrared portion of the spectrum, if we measure that in microns. And I guess what I want you to notice here is that these relative spectral response, or the spectral response functions for each of the detectors, are not evenly spaced on band center, okay? And they don't all have the same band width, right? Some are narrow bands, some are wider bands. So there's different band widths. And non-uniformly spaced. Band centers. When I say band centers, does everybody know what that means? Just the central wavelength in the spectral band. All right, and that's usually what we refer to as multispectral. Okay, so if you take this step and define a hyperspectral sensor, the difference there, if we were to draw a relative spectral response function again for the sensors, is that all of the spectral response functions are typically the same width, and they're normally, no, I'm not going to say normally, I'll say always on equal band centers. All right, so if this is 0.4 microns and this one's 0.42 microns, and this next one's going to be 0.44 microns, and the band centers will be spaced on 20 nanometer centers. Okay. And all the bands will typically be the same bandwidth.
So you mean for the hyperspectral, every detector in a different wavelength will have the same sensitivity?
No, the spectral response functions for the filters will be of equal width.
But not
I'm
equal,
not talking about detectors yet.
But not equal amplitude. Like here you said the amplitude is like equal, right? But it doesn't.
Yeah, what I've drawn here, the amplitudes, or the relative spectral response, the spectral response functions look like they're equal magnitudes. Typically, we express these as RSRs, or relative spectral response functions, where they all normalize to a peak response of 1, in which case they would look like this.
Okay.
They don't but they don't necessarily have the same absolute spectral response function. In fact, they never do, because of the detector there. All right, so that's really the difference that I'd like to put forward to you. If you have a equally spaced and equal width set of bands, then we're going to refer to that as hyperspectral.
Do you think that's more important definition than the amount of bands that it has?
No, I mean, there's no, I don't like any of the definitions.
Okay.
So if you had a 4-band sensor and it had equally spaced and equal width bands, you would still call that a multispectral sensor.
Right.
So the number of bands does come into play, but I don't want that to be the only criteria that you place. All right. So you can come up with the same functional designs for hyperspectral sensors as you had for single band or multi spectral type sensors. You could have line scanners, push boom scanners. You could have a focal plane array if you use it a little bit differently. We'll take a look at how you use a full array of detectors to do hyperspectral in a second. All right. Well, let's look at a line scanner as an initial concept drawing. All right. So the same thing to get your motion or the scan of pixels on the ground in the cross-track direction. We'll use an oscillating mirror, just like we did on Tuesday. You're going to focus that through a telescope. You're going to come through some aperture. Okay? So that field stop is what's going to define what your ground IFOV winds up being, right? Because it's the image of this field stop back through your telescope down off the ground that's going to define your pixel size on the ground that's projected down, so your GIFOV. So you want to make sure you make that that's the critical design feature in your system when it comes to spatial resolution. Now, I don't want to imply that you should always make that as tiny as possible, because you got to let enough photons come through so you get a relatively strong signal compared to the noise characteristics that you're sensing. All right, so now, once you enter into the optical, through the field stop into the rest of the optical system, typically you go ahead and collimate the light at this point, and then disperse it in some form. All right, diffraction grating, a wedge interference filter, prism, same thing that we were doing with a multispectral type of system. But now, rather than having discrete individual arrays, or discrete individual detectors that we might place at different places along that dispersed electromagnetic spectrum that we have inside the system at this point, now we're going to place a linear array, which assures that we have continuous coverage across that whole spectrum. All right, so if we take a linear array like you might have in a desktop scanner, and place it so that the dispersed energy falls from the shortest wavelength to the longest wavelength across there, because these detectors are butted right up against each other, it assures you have continuous coverage across the whole spectrum that you're dispersing at this point. So if I can come up with a means of breaking up my energy to go from 0.4 to 1 micron, and I put a silicon linear array at this point, now what I have is as many bands as I have detectors on that linear array. So it's very easy to put a 256 element or a 1,000 element linear array at that location, and now you have 256 or 1,000 bands that you can record simultaneously. So what issues might you run into in a system like this? First of all, think of the relationship between the aperture and your linear array. What do you want to make sure is true in that case?
So it's even across the aperture?
Well, remember your aperture is what you're imaging, right? So everything, all the energy comes to focus at this plane right here. Right? So that's why the converging beams cross at this point. This is your focal point of your telescope. So the amount of energy that you're letting through or at this point is going to define the spatial extent of the energy that you can see on the ground. Right? So now you're going to re-expand that, collimate it. So now you just have light at this point. Right? There's no spatial context to it anymore.
So your grading has to be perfect at putting them spectrally within the pixel size that you created?
Well, no. All right, the pixel size you created right here, right?
I mean on the linear array.
Right.
Detector size.
No, I think I see what you're saying. You know, this is going to define your spot on the ground. After this point, it's just energy. You could move this portion of the system closer or farther away, and you can let this beam expand, or get or bring it closer so it's narrower. But all you're doing is capturing energy at this point.
But your diffraction grading is spreading out the spectra, right?
Mm-hmm.
Why the aperture is actually defining the spatial resolution?
Well, if you project an image of this backwards through the telescope,
Backward?
backwards, right? So come this way off the mirror and then down to the ground. What are you going to have on the ground? You're going to have a square area. So taking it backwards, you're going to integrate the energy in that area when you come through the optical system
And
forward.
if I will move the aperture of the telescope, then we get like different area.
Well, yes, if you move the aperture of this, but now you're going to have a defocused aperture or a projected aperture on the ground. So you always want to make sure you have your aperture at your focal point of your telescope. I think the only thing that we really need to be worried about at this point, I didn't mean to drag this out a little bit, is you want to make sure that once you place this collimating lens in the path, you want to make sure that you do cover the full extent of the array if you actually want to use the full extent of the array to make your spectrometer. Right? So you want to make sure that this is not too close, so that the diffraction grading will only produce an image from here to here on the linear array. So now you lose some spectral resolution. You don't want to bring it too far away and overfill it, because now you're only sampling a portion of the spectrum. Right? So you want to make sure you match the reflection off the grading or through the prism to fill the portion of the linear array that you want to use. Okay, so does that make sense as far as a line scanner goes? What you're going to do then is, in the same way, oscillate the mirror, and you'll sample one point on the ground at a time. You'll have all the same geometric problems that you had with the single band detector, but you have this great feature that you capture now hundreds or thousands of bands simultaneously, all on the same pixel on the ground, with no registration error. All right, so an example of a spectrometer like this is the average sensor. This is a sample. You've probably seen images like this 100 times before, but a lot of times people present imaging spectrometers or imaging spectrometer data in this form, which people normally refer to as a hyperspectral cube. And what you typically see spatially on top of the cube is just some arbitrary choice of 3 bands to form a nice, pretty image. Right? But when it comes to hyperspectral imagery, typically we don't look at the imagery as much as we analyze the data spectrally. And we'll do a lot of analysis of hyperspectral data near the end of the quarter and a whole bunch of it next quarter. But just for now, what you see down the sides of these cubes is if you took a single pixel on the edge of this cube or over here, and you looked at that single pixel spectrally, going from the shortest wavelength to the longest wavelength, you would have a spectral signature that looked like if you plotted the magnitude of any one of these columns going down the side of the cube. So here it's color-coded. Blue is low magnitude, or black is the lowest magnitude. Red here is the highest magnitude. So if you plotted as a function of wavelength, the magnitude of the data going down the side of this cube, you would have a spectral signature of an object that you were looking at the ground. These bands that you see in here, that look like there's emissions or where the cube might be separated, are actually portions of the atmosphere spectrally that you can't see here. So these are the place where the transmission of the atmosphere goes to zero. All right, now, to take the imaging spectrometer and give it a little more spatial stability, the concept that we can go to is the same as we did with single band sensors again, a push boom sensor again. Let's go and use a push boom design. But now you not only want to collect spatial data across track, you want to collect spectral data at the same time. Right? So it's almost like we shifted the kind of detectors that we're using. Right? For a single pixel detector or a line scanner, we're now using a linear array. For a push broom, what we're going to do to form a hyperspectral sensor is use a two-dimensional array, a CCD array or a CMOS array. Most likely a CCD array for the materials that we need to use. All right, so the way we're going to do that is we're going to image onto the ground through our optical system a slit. Okay. So our field stop in this case isn't going to be a square like it was here. Our aperture here was just a single square. Here we're going to try and do a rectangular slit. And that rectangular slit projected through the optical system onto the ground is going to form a line on the ground. That's going to sample. So it's going to pass energy from here to here. So in this case, you want to be very generous in your optical design, in the sense that you want to use an oversized optic so that the projection of the slit through that optical system stays as close as possible to the center of that optical system. You don't want to start to get the geometric distortions and the quality distortions that you'll tend to get near the edges of an optical element, whether it be a mirror. Mirrors are normally better than glass in this case, but if you have a glass optic in there, you don't want to get near the edges. So you want to use as big an optic as reasonably possible in the system that you want to use. Now, optics are normally the biggest part of your system when you drive the size of it, so you don't want to go crazy with it. But you want to try and be as generous as possible with that. All right, now, same as we did before, we're going to then take the image of that slit, collimate it, right, and disperse the spectral data in some way, whether that be a diffraction gradient or a prism. Now, if you then go ahead and take the image of that collimated slit and refocus it, right? So now we're going to do a refocusing. What's going to happen? So if I have a slit, I collimate, make a two lens with a reflector in the middle, make a collimator, and then this final lens refocuses. I'm going to get an image of the slit again at this point in space. Okay. So if I image the slit so that I, let's see, which way is this located? So that I, I wish I could draw this. Let me go off here for a second. All right, so if we had our linear array over here, just draw a couple of the lines here. All right, so if I form the image of the slit through this second optic, so that the slit image comes right there, then what I'll do is I'll have a push broom system just like I had before, right? When I was just trying to use one band or collect one band of data. I'd have just a push broom. So this one line of detectors would sweep out this line on the ground, right? But because I'm also dispersing the data spectrally, what I'm going to have, get fancy here, I'm going to have different images of those slits at different locations on the sensor array. So one dimension of this two-dimensional array is going to be collecting spatial data within a band. The other dimension is going to be collecting multiple instances of that spatial information, but in different wavelengths. Because I'm going to have a spectrum of data that goes in this direction from, let's say lambda 1 to lambda n. Does that make sense? So you still have some geometric problems, right? If you have roll in your aircraft, you're going to get line shifting left and right. But along any single line, you're going to have very strong geometric relationships between those pixels. And now you get simultaneous resolution, or simultaneous spectral collection of all the bands that you want to sample for that line on the ground. Right? Because all your imaging in this case is the single slit. You don't have any other data coming into your system. Right? So very good registration based on color. Different sort of system, less optical elements, so these actually work pretty nicely. You have an optic which focuses on the ground, and again, what's not shown in here is the slit, but you can come in and put a wedge filter in there which disperses your energy across the two arrays. So just another optical design that you can use a wedge interference filter to disperse your light. All right, so now, let's take one more step, and this is probably the least intuitive of the sensor designs, but it's also one of the neatest ones. So I'm going to oops, go back to drawing here for a second. If I can get back to drawing. There we go. All right. Now, if I wanted to go ahead and make a full frame hyperspectral imager, I'm sort of out of luck at this point because I've already used a full frame sensor. I've already used the two-dimensional array to make a push frame. So now I want to sort of have a three-dimensional array to make a frame imager. And I don't have that technology, unfortunately. All right, so what we're going to wind up doing is going to another sort of collection system and another sort of wavelength dispersing element to make this happen. And that's going to be the use of an interferometer. Right? So the design, probably the most common design for a full frame spectral imager is based on a Michelson interferometer. Who's seen a Michelson interferometer before? All right, I'll go over it. All right, so Michelson interferometers are very, very cool. You have an optical system that's imaging an object on the ground. Okay, so let's say we're imaging this point in space. All right, you pass light into your system here. Let me just make sure I'm using the same terminology we used there. Pass light into your system, and you have energy coming in. All right, now, at this point, I have my full, whatever my optic is made out of. If it's made out of glass, I can pass easily out to 1.1 microns, further. If I want to go much further, glass starts to break down a little bit. So you could go different materials. Let's talk about that for a second. You could use just glass, optical glass. You could use quartz for your lenses. Quartzes tend to have a higher transmission as you get further and further out with shortwave infrared. So there's some point if you're trying to make a spectrometer that covers the reflective region, or what we usually refer to as the reflective region of the spectrum, usually you have to make a transition from glass to quartz at some point. All right, but for now, let's say we're just doing a white light spectrometer, or we go a little bit out into the infrared. So we can use glass. So we have a glass focusing element. We come into our system, and what I want to do is I want to take that white light and break it up so that I can then recombine it later on and try to shift the phase of the individual wavelengths of light that are coming into the system. All right? So here's what I'm going to do, and then hopefully this will make a little bit more sense in a second. I'm going to put a beam splitter in here, and I'm going to send half of the energy up this way, and I'm going to let half of the energy come through this way. All right? So I've taken my incoming signal, and I've broke it up 50-50. At this point, over here, I'm going to put a mirror. Okay? And at this point up here, I'm going to put another mirror. All right, so the light's going to come in, it's going to get split, it's going to hit these mirrors. Okay, so the black lines, we'll have them this way. Switch colors for a sec. All right, and then we're going to get a reflection off those mirrors, and the light's going to come back. And it's going to pass through in this direction. And I'm just going to use a different color for the reflection off of here. Light's going to come back. And it's going to reflect down this way. And so at that point, what will I have? What kind of light will I have at this point? I'm going to come back through and recombine.
You have white light.
I have white light again, right? I have white light. I have white light everywhere, right? I have white light everywhere if these paths are the same. Okay. Now, the minute I start changing these paths, right, I won't get perfect reconstruction of the waves that pass through. So what we're doing here is we're sort of doing a destructive and constructive interference sort of thing with the light. So if I have a wave, you know, if I represent a single wavelength, right, so let's say we're using red, right? If I have a red wave coming in, that red wave is going to pass through, and it's going to get put up this way also. Depending on where I place these mirrors, if I place them exactly the same distance away from that beam splitter, I'll get perfect reflections of the waves, and they'll recombine perfectly at this point. If I don't have equal paths, then for that particular wavelength, I won't get a complete amplitude reconstruction. I'll get a smaller amplitude reconstruction because of destructive interference. All right, now, if I come in here and I place another optical element and bring it to focus onto a detector, right, if I measure my signal, and let's assume all the optical elements are perfect here and they have complete transmission, if I have an amplitude of 10 coming in, I'll get an amplitude of 5 going each way. They'll recombine, I'll get an amplitude of 10 coming out for that wavelength. Right? Now, if I went ahead and I moved one of these mirrors, so what I'm trying to draw there is a drive motor. It's going to move that mirror one way or the other. So now, if this mirror can move, right, I could change what's called the optical path and of the green elements that are shown right here, the black and green elements that are shown going to and from the mirror. And I could change that path by a certain amount. And the difference between the path to this mirror, the movable mirror, and the path to this mirror, the fixed mirror, The difference in that distance is what's referred to as the optical path difference, the OPD. Okay. Now, if I move this, if I have 10 coming in and 5 went each way, when they come back, I'll still have 5 and 5 coming back, but they'll be out of phase. The waves will be slightly out of phase, so when they reconstruct with each other, I may only get a 9. Right? If they're more out of phase, I might only get an 8. Right? It depends on how they recombine. All right, so that's a single wavelength. Right? But all the waves are there, all the different wavelengths are there, it's white light. So I will simultaneously be collecting the magnitude changes of all the different wavelengths of light at one time. All right, now, here's what I'm going to do. As a function of OPD, the optical path difference, which is really a function of how far I move this movable mirror, I'm going to plot the magnitude of the signal that comes out of this single detector. Right? And the magnitude is going to look something like this. Right? And that's going to be as a function of optical path difference. And it'll be the magnitude of what I measure coming out of the sensor. Right? Over the past quarter and a half, you've probably seen a lot of functions that look like that in certain classes that you might have taken with a guy named Roger. Right? So, what does that sort of look like?
Sync square.
Sync square, yeah, it looks like some frequency domain function, right? Well, that's in fact what you're measuring at this point. You have the Fourier transform of the spectral signature that's defined for this point. All right, so if as a function of wavelength and reflectance, or let's just say radiance at this point, because we have radiance. Oh, that was bad. Undo? No. All right. Well, so much for that drawing. Wow, that's neat. All right. So, if I have a radiance as a function of wavelength, and let's say I have something like vegetation, right? So 0.4, 0.7, oops, 0.7, and up to about 2.5 microns for vegetation, or something like that. If I take that signal and put it into my Michelson interferometer, what comes out on the other end is the Fourier transform of that signal. So all I have to wind up doing is, as a function of, well, the function that comes out, that measured signal that comes from my detector, all I do is take the inverse Fourier transform of that, and that becomes my spectral signature. Okay. Was that?
The inverse Fourier transform?
Yes. Yeah, because my signal is going to be the Fourier transform of this. So what I measure is the interferogram. Right? This is what I measure with my detector. So to get back to my spectral signature, I take the inverse Fourier transform of that. Right? And that will give me the signal back.
So basically, the optical path distance, or
The difference.
right, the optical path difference is going to be going through the different frequencies. That's how you're constructing
Absolutely.
the Fourier transform.
Absolutely. Yeah, the difference in phase,
Right.
right, is going to convert right back to the difference in frequency.
So this will be the magnitude of the Fourier transform.
Yes, yes. But since it's real,
Right.
right, it's a real signal, you can just do the inverse Fourier transform.
It's the magnitude or the amplitude? Because if it's the amplitude, then it can be also negative.
Can't be negative, right? Because all you're measuring is a signal.
Because if you have a constructive
Yep.
interference, so you can get like a negative amplitude, but not magnitude.
Right. So
So
it's magnitude.
I think it's a measuring of the amplitude, right?
No, it is a magnitude, because you won't have a negative signal at any point. Right? You always have light falling onto your detector.
But the detector cannot give like a negative value,
No.
which means that it comes, so it will be the magnitude.
Yeah, it's kind of fun to watch this as it scans, right? If you put your eye where the detector is, what do you see? You just see a spot, right, getting brighter and darker. And that brightness and darkness is the fluctuations that you see in your interferogram. Right? When you get towards the center, where everything's in phase, you get a real bright DC component. So this is the zero optical path difference point. So you will go on both sides of that.
This is interferometer. This is the
Interferometer, yes.
Interferometer.
Yes. All right. So, if I want to now, that's a single point, right? I only have one detector. If I want to make a 2D image, I just put a focal plane here. And I collect that at many different spatial locations simultaneously. All right? So you're now, what's the beauty of this? Light comes in, all the light gets reflected, all the light comes down here, all the light hits that detector array. You're not dispersing the energy at all. There's no prism. Right? If you have 100 photons coming in, 100 photons are going to hit your detector. You don't have any loss due to dispersion, like all the prisms and the interference filters that we've been talking about to this point. So the signal and noise ratio on these systems can be through the roof, right? Because you got all these photons. That's fantastic. All right. There's always a but, right? So what's wrong with this kind of a system? And I hate these systems. And here's why. All right? Great signal noise ratio. And there's two very distinct schools of thought. There are people who think these are the greatest things in the world, and there's people who absolutely despise them. I'm on the absolutely despise them side. You have to move that mirror, right? It takes physical time to move that mirror. Why is that a problem?
It'll get bad over time.
What's that?
There are two problems, right? So it'll get bad over time at moving the mirror perfectly.
Now let's say we hired the best mechanical engineers.
You have to wait until
You won't
the
rest.
scanner and
Perfect.
everything.
Yeah,
You have to wait some time to make the scan.
does it give you any smear or something like that?
If you're moving your sensor in an airplane, you can't stop, do a scan, and then move on. So what you're doing is, as you're making the scan, you're changing the object that you're imaging because you're moving your detector. All right? So let me just check your expression here. Oh, absolutely. All right, so if I change the object I'm looking at, right? Let's say I go from a white car to the black asphalt next to it. Right? What's going to happen to the number of photons going into my system? If you went from a white car to black asphalt, the number of photons is going to get smaller. That's going to be a change in the number of photons going through. It's also going to be a change in the number of photons going through the rest of this interferometer. What are we measuring here? We're measuring a change in the magnitude of the signal. If we're changing the magnitude of the signal because of optical path differences, and we're measuring the change in the signal because now we're looking at different objects, that's going to introduce different little wiggles in my interferogram. Right? Now if I inverse Fourier transform that, what am I going to get the spectral signature of? That's a perfect answer. You just shrugged your shoulder. I think you just shrugged your shoulder. All right. I don't know what you're going to get the spectral signature of. Because at any point in time, when you had any particular optical path difference, you could be looking at a different object on the ground. Yeah.
But why you need to change the optical difference part anytime? You're not just changing it once, that there will be some difference between the fold mirror and the movable mirror, and then that's it, and it's not going to move anymore.
Oh no, it's you need to go through a full scan in order to collect all your data. So in other words, I have to take this mirror from this point
to get like all the spectrum?
to get all the frequencies in the interferogram. All right, I have to move the mirror from here through a 0 optical path difference to so a negative optical path difference to a 0 optical path difference to a positive optical path difference. I need to move through that whole range
the
of
minimum frequency to the max frequency, and then like white is the 0.
Well, no, I mean it's not any particular color. It's a frequency at that point. Right? That's the DC component when it's at 0. DC component of the interferogram.
And you have to do it for every spatial area.
Yeah. So then I would scan backwards. That would be another interferogram. Then I'd scan this way, another interferogram. So when you watch the data coming off this, the interferograms flip back and forth, so you have to reorient them before you do the inverse Fourier transform to get your spectra to come out correctly. But because this is on a moving platform, you're going to have problems. All right, now, first time I saw this design, I was at a design review meeting for a system that was actually built already. And they were presenting it to the person who was going to use it. And they would present this thing as the best thing in the world. And I was sitting there scratching my head. You know, I was right out of school, didn't have a lot of confidence in what I was about to say, but I said it anyway. I said, that's not going to produce the data that you're telling me. And you know, the engineer who was presenting all of a sudden just went, what do you mean? Because I think they knew, right? So then I explained what was going to happen here, and the customer just got all upset, and they sent them back to the drawing board. All right, so it was one of those moments that you were right, and you're going to have those, right? So have confidence in what you're believing, and go out on a limb. And if you're wrong, they remember that for a long time. If you're right, they remember that for a long time too. So you have to take that chance. All right, so all right, so how do you solve this? I should have just went through these slides. This kind of tells all the story I was just telling. But here's how you solve it, right? You make your optical system continually point at the same object on the ground as you fly, right? So if I'm flying an imaging spectrometer like this that's based on an interferometer, the only way that I'm going to trust this data is if I fly in this direction and I take images of the point on this roof from all these different locations while I'm scanning my mirror. In other words, my object's not changing, right? That's not true, right? Because the projection's different. But this is the only way you're going to get that, right? Be able to use these systems. So, what do you think a very common use of a system like this might be? What's that?
When you're not moving.
Well, no, but from an airplane, what do you think you might want to do?
Looking at something in particular, not making like a big ground scan.
Yeah. So, you know, people will typically be very interested in a very specific target on the ground that they want a signature on. So these systems will work like that. If you're, let's say you're trying to, I don't want to pick on Kodak anymore because they're in enough trouble, but if you look at one of their stacks up at Kodak Park by Route 104 and you know it's billowing out some big cloud of smoke, you may want to look at that cloud of smoke and determine what it's composed of. Right? You may want to determine what chemical emissions are coming out of there at a particular time. So then you focus your system. In that case, you probably use a long-wave infrared system to do gas detection. But you probably focus the system on the smokestack and watch what's coming out of there. Okay? Now that's another problem. Right? What problem's there? The gas is moving. So now my target's moving. My airplane's moving, my target's moving, my mirror's moving. So that was my second go out on a limb issue. Was I said, so they said, okay, well we're going to use this for gas detection. I was like, wait, you can't do that. Right, so if you want to read at some point, there's things you do that you're not always proud of, and this is one of them. Let me just pull up my web page here for a sec. I put out a paper right after that meeting. Well, no, a couple weeks after the meeting. I had to do a little bit of work first. So one of my good friends, Herb Mitchell, and Terry Hammer, and Paul Lewis, and myself, I was sitting at this meeting. I was the only one who spoke up, and these guys all agreed with me afterwards. So I felt good. At least somebody else in the room was doing this. But what we did was we had a Fourier transform infrared spectrometer, and I have it upstairs actually. If anybody wants to see this instrument, it's kind of cool. And what we wanted to do is we wanted to produce a moving signal. So I just want to get to this picture. All right. All right, so we went back to our offices and we said, okay, how can we produce a moving cloud of gas? And so Herb Mitchell is a real wacky. Herb's probably close to 90 right now. He's still working. He's never going to retire. He's one of these guys who has just ideas that don't come out of normal people. So I said, all right, well, how can we produce a moving cloud of gas? He goes, well, let's go outside. Let's take my Ford Expedition, and let's put a dryer vent hose on the exhaust, and I can inject acetone inside that with a needle, and the hot exhaust will vaporize that, and then we could hold it up in the air like this, and we can take images of it. And I was like, and we're going to be breathing in the acetone? And he's like, yeah, don't worry about it. You can take a little bit of it. I was like, no! All right, so Herb actually is now colorblind, not because he was born that way. It was because at some point, you know, back in the 1950s when he was in the Navy, he got to play with these things called lasers, and he thought looking into them was very cool, and he actually got rid of all his color perception. Try driving with a guy who has no color perception. When you get to traffic lights, it's a very scary thing. And I went to Hawaii with him once, and he was pretty good because he knew the red light was on top and the green light was on the bottom. In Hawaii, for some reason, they turned all the traffic lights so they were sideways. The most terrifying experience of my life. Because he was going through red lights and stopping it. It was terrible. All right, so I said, okay, well, what else can we do that we're not going to, you know, have cancer in 3 years? So he said, well, let me go to the kitchen for a second. And he comes back with a grease splash guard. We had a kitchen in the place where we were working. And you ever see those things you put over the top of a frying pan so the grease doesn't find out? It's like a fine mesh screen. He's like, we can use this. And I just shook my head, so okay, how are we going to use this? Well, he's like, well, I'm going to take a drill, and I'm going to cut out portions of this screen, and I'm going to put a bolt in here, and he's pulling all this stuff out of his desk, and you know, so he took out a little knife, he cut this and doing this, and I'm going to put this on the end of the drill, and then I could do this. And he turns it on, and this thing starts spinning. I'm like, okay, what's going on here? He goes, well, if we look through here with the spectrometer, it'll look like we're looking through air. If we look through here, it'll look like we're looking through a cloud. And then it'll look like air, and it'll look like a cloud, look like air, and look like a cloud. I'm like, that's brilliant. Right? So what we did was we put the spectrometer right here, turned on the drill, and we're able to look through clear and screen and clear and screen. So we were able to change the optical signal that was coming into the spectrometer. So you sort of produce something that looked like a moving gas as a symbol. And it turned out that, you know, when you look through this thing, and you didn't look through this thing, I think we have graphs in here, you actually introduce features into your spectra that weren't there before. We were looking at a black body. There's the black body at the temperature we were looking at. And depending on the speed that you spun that at, you were able to produce different spectral features that weren't really there. All dependent on the speed. So then he decided, a little later on, oh yeah, there's pictures. He said, well, let's, I think he just wanted to use his bandsaw. So he put all kind of different shapes that he spun on this drill. We did this for a couple days because we were just having fun at that point. All right, so we put that paper out right after that. So now the the poor contractor who was making this detector was like, oh, yeah, right? But this is $1 billion sensor that they built, and it's a beautiful sensor. And if you use it on still objects, it works incredibly well. If your object's still and you're not moving, these things are fantastic. I use one all the time. I have one upstairs. It's in a case about this big. It's called a micro FTIR, and I measure ground spectra in the thermal infrared with this instrument. And we'll actually go over how those sorts of things work a little later in the quarter. So these are great for that. But when you start putting them in an airplane, you form your own opinion. I don't want to influence you too much. But I don't think these things should be flown in airplanes. Okay, so let's go back here for a second. So yeah, here's a little illustration of what you might see when you fly. All right, so making a full frame hyperspectral imager is a tough thing. And to do it for still objects and still platforms, it's very doable. I think Roger actually has a white light imaging spectrometer based on this sort of design down in his lab. I almost got that one sensor that I was just talking about. I almost got it donated to RIT when I first came here because the folks stopped using it, but for some reason they couldn't bring it over here. I don't know why. I forget exactly what the reason was, but we would have had that one too. All right, so now let's talk a little bit about some of the problems that you have with these types of sensors. Even the push broom sensors that we were talking about earlier. All right, so if we're looking at an object on the ground through a push broom type hyperspectral sensor, and we reproject that slit down to the ground and sweep out that spot on the in the across track direction, go through and do everything that we said. If everything is aligned perfectly, what I just told you about how these things work, it'll work just perfectly. But there's a problem that comes into play. The minute you get a little bit of misalignment between any of these optical elements, the image of your slit is going to start to bend one way or the other. Okay? So unless you have these optical elements in absolute perfect alignment, and I mean no error at all, you're going to have some sort of bend to the image of it. So your ideal projection would be a nice rectangular picture of a slit, but your actual projection is probably going to look something more, and this is exaggerated. It's going to look something more like that. And you can spend all day long and try to align this in the laboratory, but the minute you start moving it around and vibrations in the sensor, you're going to start to see this sort of deformation in the image of your slit. Now, people usually refer to this as spectral smile. Okay, and John goes in his book. If you read through on this section, he goes through a couple sentences why this is called spectral smile. It really looks like a spectral frown. Going that way, it'll typically bend in the downward direction. But people normally refer to it as spectral smile. And the problem with that is, if you look in some of these cases here, if you have this bend, what's going to happen? I'm dispersing the spectral elements in this direction, in a vertical direction. Spatial elements in the horizontal direction. Right? If I bend that signal, I'm going to be sampling on a particular row data that is actually above or below that point. Right? So I'm going to get a misalignment, and a particular spot on the ground will be measured in this row, or in this spatial position. Right? And if another spot on the ground will be in this spatial position. But you can see that if I look at that line projected on the ground, I might have different spatial positions projected in different colors at different times. So I'll start to get a misalignment between the actual spectral data and the spatial data. Right? And this can get worse, right? You can not only have slight misalignments with the optics, you can start to get some skew also. So you can spectral smile can take on all different kinds of shapes, and that missampling is a huge problem. So there's no system that's being flown that doesn't have this built into it. So whenever you work with hyperspectral data, whenever you get a detecting array or a new sensor that comes along that is based on this kind of technology, you want to make sure you get from the manufacturer, the person that created it, a characterization of the spectral smile, because you need to go ahead and resample this data, put it back in the right places as a function of position across the line if you want to get your spectral signals right. And that's not always hard to do because you're going to fall across, fractional portions of detectors. Right? It's not like this is huge where you have a misalignment here of 20 or 30 detectors. I mean, that's really bad. It's only 2 or 3. But you need to be able to bring that back together, or at least understand that that's a problem. Okay? A lot of times what folks will do is rather than try to correct it, what they'll do is they'll bin spectral bands together to sort of smear it out. Right? So imagine you collected 256, this was a 256 by 256 array, let's say. So you have 256 pixels across, 256 spectral bands in this direction. Right? If your problem didn't really require 256 spectral bands, but you can get away with, let's see, what's that divided by 3? 80 something. All right, so let's say you can get away with 80 bands. Well, what you could do is you could average 3 rows of this, and now have a wider band, okay, and reduce the effect of that spectral smile a little bit. Right? You're still going to have it because it's still going to cross those edges of those integrated areas, or the three line integrated areas, but you start to reduce them. Okay? A lot of times you'll over-design your system, and let's say you want to make a 256 band system, you might put a 1024 by 1024 array in there, so that you know beforehand you're actually going to combine lines. Okay? And so that's a very reasonable thing to do in your design to reduce the effect of spectral smile. Want to take a break? Or want to go a little bit and enter it? How you feeling? Everybody's up. Always good.
So are you saying that you start with spectral smile, but then it gets worse as well?
Well, I mean, you always want to start with no spectral smile, right? If you're designing in a lab, but the minute you start moving the system, you're going to start to get misalignment between your optical elements.
But I mean, the second you put it up in the air, it's not going to be the same smile that it was before it was up in the air, right? Like just from the...
If everything was rigidly mounted, yeah, it should be the same. And the same misalignment should happen. But what I'm saying is, your misalignment will get better or worse, most likely worse. But it could vibrate the other way, and it could get better at times. But it's going to change. It's going to change. But people design these so that it is pretty rigid. But the optical alignment, even in a laboratory, is very, very tough to do. Because these detectors, remember, are 10 microns on the side. So being able to align to that sort of accuracy is very tough.
Over time, do they start binning them more and more? Or do they not get that bad over time?
I would say, in the majority of cases, people don't look at it that carefully over time, more than anything else. But yes, it should be brought back in the lab every so often, and that spectral smile should be remeasured. And that's the other part. I mean, if you have your own detector, then it's up to you to do that recalibration of the detector on some regular interval. If it's somebody else who's flying for you and you're just getting data, you really need to understand how often they characterize all these things on your sensor.
So there's onboard characterization of the smile?
I haven't seen anybody do an onboard spectral characterization. I mean, that would imply having a monochrometer and a calibrated light source and everything on board. Yeah, it's just...
More elements.
What's that?
Seems like for everything, the more elements you add to it, the more space.
Oh, absolutely, and size, sheer size. Because we'll talk about calibration here in a second, but entrance aperture to these devices are usually pretty big. Okay? And that means you have to have integrating spheres that have openings that big, which means they're about that big. So that's when you're having problems.
So yesterday at the seminar, were you there for the talk?
No, I wasn't there yesterday.
So he was talking about a similar design. He was saying that the spectrometer or whatever sensor that they were using was built at NASA JPL, and that they got to what kind of smile of 5% of a pixel, I think he was saying.
That's tight. That's
But
very
so those numbers are just for the lab, right? That's gonna change when they start buying.
Absolutely, absolutely, it's going to change. And 5% is something you could achieve with a NASA budget.
Right, right. I'm sure that that can be possible.
Yeah.
But even then, you don't really know what you're gonna get at once.
Once you put it on the air.
Right.
We'll keep going? All right, let's keep going. All right, so calibration. We're going to talk about, calibration is what we're all about here. I mean, in the remote sensing lab, we've really kind of, our initial, if you want to call it reputation in the industry, was as calibration folks. We did calibration for the Landsat thematic mapper thermal channel for the past 30 years or something. Well, no, it's not 30, 20 years probably. No, it's probably 30 years now, since mid-1980s. And we've always, whatever instrument we built, we've always built the instrument with the concept of calibration in mind, because we always want to get the best radiance data that's possible. Lots of sensors, your cameras that you have, right, they take great pictures, but they're not calibrated. A lot of systems that are flown produce fantastic imagery, but it doesn't come along with calibration data. There's a lot you could do with uncalibrated data. You get very good relative comparisons between targets on the ground. And I don't want to say uncalibrated data is useless by any means, but if you can go to full calibration and do it within your budget, then why not? I mean, because then you have the capability of doing a real, a quick and dirty sort of analysis where you don't take your data to calibrated radiance and get an answer, a good answer for a particular problem that you're looking at. Is this grass healthier than that grass? Or is this stand of trees healthier than that stand of trees? You can do that kind of thing without absolute calibration. But if you wanted to come in and you need to know the temperature of an object on the ground within 0.5 degrees Celsius, then you've got to begin to think, I need absolute calibration on board. So there's two types of calibrations that come into play when you talk about sensors. One's geometric calibration and one is radiometric calibration. In this class, we're going to talk mostly about radiometric calibration. Geometric calibration, we push off to the photogrammetry class. And that's where you could understand that, as well as the 3D geometry class that's going on right now that Dr. Remy's teaching. Anybody taking that class? The 3D one? I'll take it next year. Awesome class. Although I heard the amount of work in it's amazing this year. All right, so we're not going to talk about geometric calibration in any sort of depth here. But just to let you know, there's two types of things that are referred to when it comes to geometric calibration. One's called internal orientation, one's called external orientation. Internal orientation refers to the geometric understanding of the device itself. You understand the focal length, you know where all the pixels fall, you know where all the pixels are on the focal plane array itself, and you understand everything that's going on inside the camera. External orientation says, okay, now let me take that data and project it down onto the ground. Right? So in that case, you have to know how your sensor's oriented in the air. That's the roll, pitch, and yaw we talked about the other day for your aircraft. You have to know really the topography of the ground and the height of every point on the ground. If you go back and think about the relief displays and stuff that you did in the photogrammetry lab, you really had to know the height of things to be able to, because scale changed as a function of position. Right, so those sorts of things are the things you need to worry about when we talk about geometric calibration. But again, like I said, that we're going to do later on in the photogrammetry class. We can go on and take that. All right, so what we want to talk about here is radiometric calibration. All right, and that all really starts off by understanding, some of the concepts about your sensor. And one of the most important things that you want to understand about your detector that's inside your sensor is how it responds as a function of wavelength. And the relative spectral response function is typically the term that we use in specifying that. And what it is, and you've seen this in radiometry, I'm sure, is how that detector responds to incoming energy as a function of wavelength. All right. Now, the things that you'll typically see in most multispectral sensors that are out there, so sensors that can have different bandwidth and non-uniform band centers that we just spoke about, is you usually see a concept called the band pass, or the bandwidth, for that particular band that you're looking at. And tell me if you've already seen these concepts. The bandwidth is normally referred to as, or by a term called full width at half maximum. So if we measured a spectral response function for the detector, right, and as a function of wavelength, we have a peak spectral response right here, where it hits one, and everything is measured relative to that. The full width at half maximum is the point on the rising end and the trailing end where it equals half, right, half your maximum response level, and it's the distance between that and wavelength. Right? So that you can go ahead and measure on a monochromator. Right? You can take your detector into the lab, you can place it in front of a monochromator, expose that detector to different wavelengths of light by allowing the monochromator to move through its full range, and record the signal that comes out. All right, now, one of the problems is once you start getting hundreds and thousands of detectors in a hyperspectral system, that becomes well, a big data management problem more than anything else to keep all those relevant spectral response functions around. So shortcuts are taken sometimes. And don't do this unless you have to. And it used to be that you have to because this was a lot of data to keep in a computer, but now it's not. So I would encourage you guys not to do what I'm about to show you in the future, but really just record these relative response functions for every detector they have. But it could be that this was your relative response function as a function of a discrete set of wavelengths that you exposed your system to. This was your signal level as a function of wavelength. And a lot of times in a hyperspectral system, what they will do is they will fit a Gaussian to that data, right? Even though it's not perfectly Gaussian, down here you can see a fit Gaussian, the best fit Gaussian through these squares that falls on that data. It's not perfect, but it's very close, right? And folks will usually report the band center, the mean, the Gaussian, and the standard deviation, and with two numbers be able to define your spectral response function. Again, unless you have to for some reason, because you're limited in storage, I would just keep your actual data around when it comes to relative response functions at this point in time. All right, now, there's problems in defining this because when you look at a particular band, right, you measure its relative spectral response function for a particular type of detector, there will be portions outside the bandpass that you're interested in where that detector material is still sensitive. So for instance, you know, if you take your digital camera and you take a picture with it, things that look blue in the scene look blue, things that look green in the scene look green, things that look red in the scene look red, everything looks the color it should on your image. Well, that's only because something was done inside the camera. And the reason that happens is silicon actually is very sensitive even out into the infrared portion of the spectrum. Right? So in front of your Bayer pattern that specifies the red, green, and blue pixels that get imaged in your camera, there's another filter called an IR reject filter. Right? And that IR reject filter blocks the incoming infrared radiation from the world. You don't see it with your eyes, but there's lots of infrared radiation. It blocks that so that it doesn't oversaturate the red channel of your detector, right? So so you might think of it like this. This might be the response of silicon out in the near infrared. If I didn't block that energy from coming in, then I would actually record that with my red detector and record it in my signal, right? That's called out-of-band radiance measurement, right? When you measure energy that's outside of your band, right? That's an out-of-band measurement. To come back with the energy in your band, what you typically want to do is you want to measure the full spectral response, right? So if you're with your wavelengths going from 0 to infinity, measure that signal, right? Then measure the signal in the bandpass you're interested in, and then the difference between those, right? This includes the out-of-band radiance. This includes just the in-band radiance. What you can do at that point is you can come up with a way of saying how much energy outside of the bandpass that I'm interested in is going to come into play when I look at my signal. And you want to minimize that as much as possible. If this number is significant, right, then you've got to be absolutely sure that you block the energy that's outside that band. So that's one of the things you want to understand about your sensor, how much of that exists. All right, so how do you go about measuring this kind of stuff? And I don't know if we'll have time at the end here, but again, I could show you this kind of stuff up in our lab at some point if you want to see the the magnitude of this equipment, just so you have a better feel for what it looks like. But what you need to do in sensor calibration is you need to provide your system with a uniform field of incoming radiance. Okay? And in radiometry, you go to the lab and use the integrating spheres?
We talked about
We talked about it, but we didn't feel it.
Oh, you didn't use them? Okay. All right, but so what you want to do is to present that uniform field of light. Is an integrating sphere is one of the best ways to do it. You got a nice diffuse coating inside of here, usually made out of spectral line. And as long as spectral line is never touched or mechanically manipulated in any way, it tends to be very diffuse when it comes off the production line. Light bulbs inside of there, out of the field of view of the sensor, can provide different amounts of energy. So typically in a large sphere, you might have 10, 15 different bulbs inside of there. And what that lets you do is it lets you turn on each bulb one at a time, and in combination, if I turn on one bulb, I get one particular radiance level out. If I turn on two bulbs, another. If I turn on three, another. And if you vary the wattage of these bulbs, you can get a whole big range of different radiance values that come out of there. Now each of these bulbs are typically NIST-calibrated bulbs. So you buy this bulb. That bulb has actually made a trip from the manufacturer to the NIST optical characterization facility, where they, as a function of voltage, tell you exactly the radiance that's coming out of that bulb. So these bulbs need to be very tightly controlled with a uniform power supply, and you've got to set it to the very specific value that NIST said to get those radiance out. And if you do that, you can get a very controlled signal out here, a NIST calibration certified signal out of the sphere. All right, now, this entrance aperture to that sphere has to be significantly larger than the input aperture of your system. Right? So for instance, I mentioned that we built a hyperspectral system, I think last class. It's a sensor up in the, you can see it up in the lab, it's called MISSI. And that had a 6-inch entrance aperture. So that meant we had to have at least a 6-inch opening in our sphere. Right? Now you don't want to get too close to the edges of the sphere because you start to get some vignetting sorts of effects unless you align everything perfectly. So you want to get a significantly larger one. So upstairs we have an integrating sphere that has a 10-inch opening. So the sphere itself probably is about almost 3 feet in diameter with a 10-inch opening on there. All right, so you want to make sure your sphere is large enough that you can look inside. So if this was the fold mirror and the line scanner, you want to be able to look down into that system. And then you just go through the optical system and you know the radiance that is at this point. Right? You can measure your signal at this point. And now you can start to measure all sorts of things about your particular detector. But the key is to start off with this uniform field. All right, so ideally what you want to do is you want to present your detector with a whole bunch of different radiance levels and record the signal that comes out, usually in a digital count. Right? So if I can record digital count as a function of different input signals, and I plot that data, and it makes a nice straight line, right? You keep your fingers crossed so you get a nice straight line, and typically most modern detectors respond very linearly to input radiance. You can then measure the gain and the bias term for your particular detector. You can do that for a single detector, you can do that for a linear array, you can do that for an entire two-dimensional array of detectors if you'd like. Right? And you can get a separate gain and bias value for each one. You certainly never want to make the assumption that two-dimensional array detectors all have the same gain and bias across all the detectors. For a couple reasons. You're going to have some variation in the material across the detector material itself across that array. That's going to cause gain and bias differences. But even bigger than that is the optical throughput is going to change as a function of position for your particular system. So you might get lens fall off and things like that that occur And by using gains and biases on an individual detector basis, you can correct for all that and still get an absolute radiance measurement at every point. A lot of people overlook that and they come up with one gain and bias for an entire system, but essentially you're going to have G and B as a function of X and Y in your final digital image that comes out. So you want to, if you are using a CCD or a two-dimensional array-based system, make sure you go ahead and do that for each of the individual detectors itself. Okay, now if you have a thermal sensor, right, so it's sort of a similar design, and what you would do in that particular case is your source is no longer a light, a bulb. Usually a tungsten halogen bulb is what we use. But in this case, you're going to use a black body. Right? Now, a black body is typically it's a brass plate that's painted with a very high emissivity paint, and usually you can get emissivities on the order of a couple nines if you use the paint properly. I don't know how much you guys know about infrared phenomenology, and we'll talk a little bit more about it a little later in the quarter. But in addition to paint being high emissivity, there's other things you can do. So if I had a flat brass plate and I painted it with a high emissivity black paint on that surface, okay. Like I said, I can get a couple nines, and it's sort of funny. The best paint to do this with is Krylon. Okay, you get it at Home Depot, right? And it's called Ultra Flat Black. Right? So never before can you get a highly radiometrically desirable item at Home Depot. Right? But Krylon Ultra Flat Black is the best paint. If you ever want to do this with, this stuff's awesome. About 9 months ago, about 9 months ago now, we went over to Home Depot and there was no Ultra Flat Black at Home Depot. So we came back and we started looking around the web and nobody had Ultra Flat Black anymore. We called Krylon and they said, oh, we stopped producing that because it was too delicate of a paint. If you touched the surface, you could see the scuff marks on it. And we're like, wait a minute. So we explained to them what we were doing with this paint, and they sent us the last 4 cases that they had of it. So we have the last 4 cases sitting in. I'm hoping at some point they go back and they start producing this paint again. But if you ever need it, you have 4 cases, and we won't charge you that much. So that's great, and this works okay. But it's very hard. It's very delicate. If you touch this stuff, and I don't know, pick on you guys. But the first thing you guys do when you see something, you go, oh, check that out. And you touch it. Right? So that happens all the time, and we do it also. Now, the other thing you can do is you can roughen the surface. Okay? And what's the whole goal here? The goal is to reflect no photons, right? High emissivity, or an emissivity of 1, means the reflectance is 0. So all the photons that come down onto here, I never want them to leave again. So if I paint it with a paint that's emissivity 1, that'll happen. But if I don't have that, if I texture the surface, and particularly if I sawtooth the surface, right? So let's say I sawtooth that surface. Now let me blow up one of those areas like this. All right. Now, if I paint that with a reasonably good black paint, let's say it has an emissivity of 0.96. Okay, so not 0.999, but 0.96. If I have a photon, or a set of photons that come down like this, where's it going to reflect? Well, it's going to reflect here, right? And then in this case, the way I've drawn it, it's going to reflect back out. Right? And that's bad, right? Because a photon coming in left. So that means the reflectance isn't 0. But if I could design that V to be a particular angle that when I have something coming in, and I'm not going to be able to draw this because I never can, then it does this, and then it does this, and then it does this, and then it does that, and it gets trapped in there, then it never leaves, that V in the surface can effectively increase the emissivity of it. So a lot of times what we do, instead of just taking a flat black or a flat brass plate like that, we groove it out to make those V's on it. So you'll see that in a lot of black bodies that you can buy commercially on the market also. Okay, so that's your source, right? You apply an electrical current to the brass plate, and it's a resistor. It heats up. You want to design the circuits on that black plate so it heats up nice and evenly, right? That's doable. And what you can do at that point is, as a function of voltage, you can control the temperature of that black body source, right? So now it's a controlled source. You want to know its temperature, right? If you know its temperature exactly, then you know its radiance exactly. Just go through Planck's equation, you know the radiance leaving the surface. All right, so now I just use that as my source, and typically the way we make a large aperture black body, these are hard to make big. They're easy to make about 4 inches by 4 inches. We do that all the time. But if we need a 10 inch by 10 inch one, well, they make those. They're really, really expensive, like on the order of $120,000 sorts of expensive to make those. Outrageously expensive, because who wants one of those? Right? So it's just sheer numbers. But what you can do is you can take a smaller one and you can expand the beam. Right? So if you run a black body over here and go backward through a telescope, right? Because what does a telescope do? A telescope takes rays from infinity and focuses it on your eye. Put a black body at that point, then you get rays in infinity in an expanded beam. Right? So actually upstairs in our Cal lab, we have a piece of PVC pipe, right? That's about maybe 15 inches in diameter. And inside that pipe is a telescope, is a fold mirror like this and a parabolic mirror at this point. And so if we drilled a hole in the side of the pipe, we put a black body on the outside of it, and we get collimated energy coming out of that point. So it's really easy to make one of these by yourself. Right, so, but that exactly does essentially the same thing that the integrating sphere does. Gives you a nice uniform field of thermal infrared energy, so that you can go ahead and figure out the gain and the bias term in exactly the same way. The way you're changing radiance here is you're just changing the voltage that you're applying to your black body source to change its temperature. So you know, as a function of temperature, what you're getting out, or radiance. Then you can go back and compute your gain and bias exactly the same way. Right. Now, if you want to go ahead and do that spectrally, I thought there would be a picture there. If you want to do that spectrally, you have to add one more piece to the puzzle here. And that is, you need to illuminate your sphere, or take the illumination from your sphere and run it through a monochromator. Okay? So now if you have a nice uniform field, and you run that through a monochromator and you look at it with your detector, as you're changing the wavelength, you'll get relative spectral responses and relative gains and biases for the different wavelengths just by running that back through a monochromator.
Should you get 0 for everything that's not the beam or the wavelength the monochromator is allowing through? Am I asking that question correctly? Do you see what I'm saying?
Ask me one more time.
So if you put the light through a monochromator, then you're saying only one wavelength.
Yes. Everybody always says one wavelength.
One wavelength.
Yep.
Okay, so if you have a multi or hyperspectral instrument, then there should just be one set of detectors
That are hot at that particular point.
right. So
Yep.
then you would be able to see if other detectors were lighting up, if there was some kind of
Leakage.
leakage.
Absolutely. Absolutely. Now the thing is, you'll never get one wavelength because the monochromator is based on a slit that has a physical width to it, so you always have a band width to the energy that's coming out. You just want to make sure that's significantly smaller than the spectral delta that you have in your system itself. So if your linear array that you're sampling the spectra with, 10 micron pixels, you want to figure out what that 10 micron pixel corresponds to in a bandpass, and then you want to illuminate with a slit through the monochromator that's smaller than that. If you over-illuminate, then yes, you're going to get all kind of pixels like that.
That's like a good test of your diffraction.
Absolutely. Absolutely. All right, so the idea in the end is to take digital count and have that be a function of radiance. And if we know the gain and bias, we can do that. Okay, so it's easy to do in a laboratory. Right? Doing it on board a sensor is a big deal. Being able to take some of this equipment, these integrating spheres and things like that, and put them on board, an airborne or a spaceborne sensor tends to be difficult. So what you can do is you could improvise and try and do the best things you can. All right, so here's one idea. If this is an optical system for, let's say, a spaceborne imaging platform. So here's your telescope, your detector's back here, you got a scan mirror over here, let's say it's a land scanner in space. Typically that would look down at the ground. All right? Well, how about doing this? Have a panel that's a piece of spectral, right? A nice diffuse white panel. And every so often, rotate this thing from here, rotate it into the path. All right, so now I can't see the ground anymore. All I see is this white panel. Well, if you can orient your spacecraft in such a way that the sun then illuminates that panel, you have nice uniform illumination coming in that's collimated. It reflects off this diffuse panel, comes up through the scan mirror into your detector. You know how many miles away you are from the sun, right? So you can use all the radiometry equations to figure out how much energy is coming off that diffuse reflectance panel into your system, right? You have a very nice calibrated light source, provided you believe we know the spectroscopy of the sun. So you can do those sorts of things on board. So you were asking earlier, can you do this stuff on board? It's hard to do it the same way you do it in the laboratory, but you can make some improvising assumptions and do this. Now, here's the nastiest thing that I've seen happen with something like this. This panel goes into place, you do your calibration, and the motor breaks. Now you never see the ground again. It has happened more times than you might think. All right. So, in that particular case, if you have that flat panel, that diffuser, you know the exoatmospheric solar radiance at any point in the orbit around the Earth. You know the angle with respect to the sun and the diffusing panel, so you can get the amount of energy that's going to reflect into that direction of the inside of the detector itself. You know the reflectance of the panel. You measure that on the ground. You got to hope that doesn't change, and most of these things do change very slowly over time. So you can't always be assured that you know R, which is the bidirectional reflectance distribution function at that point, and then you convert that to radiance, your input signal. Now, one of the other things that you always need to be a little bit careful of, and I've mentioned this a whole bunch, is signal-to-noise ratio, and how do you measure signal-to-noise ratio? And how does that come into play? Well, with a reflective sensor, typically what you would do is you would close the aperture and see the signal coming out of your detector. Right? That's usually called your dark noise, or your dark current. And if you measure that noise, and you know the gain in your system, then you can convert that noise level, right, which is usually in a voltage, you can convert that, or digital count, you can convert that through the gain into what's called a noise equivalent radiance value. Okay? That's how much radiance is there just because the system is sitting there operating. Not necessarily because there's anything coming in, because you block the entrance aperture. This is due to electronics itself. All right, now, once you know that noise equivalent radiance, you compare that to the radiance of a particular target that you might be interested in. Right? So for instance, in this particular case, the equation here shows top of the atmosphere reflectance of 18%. Right? If I have a solar declination of 30 degrees, we compute the top of the atmosphere spectral radiance to be this equation right there. Right? Take the exoatmospheric solar radiance times that declination angle times the reflectance of the target that you're looking at, convert it to radiance, multiplied by the spectral response function, you get out radiance. Right? So with those numbers and a known spectral response function, you can go ahead and compute that. Well, that's the top of the atmosphere radiance for an 18% reflector. Now, if you know that, and you know the noise equivalent radiance, which was the noise that you measured, the dark current divided by the gain, then you can go ahead and compute the signal-to-noise ratio for an 18% reflector. Right? That signal-to-noise ratio is going to change, right, for every signal level. So you can measure it at many different levels. And you can report back to the person who's going to use your system the signal-noise ratio as a function of reflectance. And that's a very powerful thing to have, because if you have a sensor now and you want to go do a measurement of water in the near-infrared wavelength bands where there's not a lot of photons there, you want to know what that signal-noise ratio is to know whether or not that sensor is going to be sensitive enough to see the small change in reflectance of the water surface that might result because of you know, a phytoplankton level or you know, something that you're trying to measure. You want to know if you can ever hope to see that, right? So not knowing the noise of your system, really you're kind of using your system blindly. And a lot of times you'll see a lot of papers out there in literature where people say they can see things and they don't report anything about signal-noise ratio of the sensor they use. So you always have to question about whether I actually saw something. Okay. For a thermal infrared sensor, you do exactly the same way, right? But typically you don't want to use dark current, right? Dark current in the sense of a thermal infrared sensor really is a very strange meaning. That means you're looking at an object that's at absolute zero. And that's typically not going to be the case. So what you want to do is you want to look at an object at a temperature that's similar to the temperatures that you're going to be measuring with that detector. 273 is 0 Celsius in kelvins. And you can do that same calculation. But this time, measure the signal level for a 273-degree object and characterize the noise on that particular object. And then relative to that, if you're measuring now things that are warmer than 0 degrees Celsius, you can compute signal-to-noise ratios in that case. Okay, so let's stop there for today. What I'd like you to do, there's a section in the text, section 6.5, which is called a sensor case study. This describes something that Tim Gallagher, who was one of our lab technicians here for a long time, and John Schott did when they both worked at a company called Calibration in Buffalo before they both came here to RIT. They had to do a redesign of a thermal infrared line scanner. It's the one I told you about, the Bendix line scanner that we used to fly. They had to do a redesign of that to get a smaller spot size on the ground. This particular section will walk you through the kind of analysis that you would have to do and use the radiometry that you learned last quarter to decide, all right, if I want, just to give you the highlights here, this particular sensor had a 2.5-foot spot size on the ground, and they wanted to make it a 1-foot spot size on the ground, but they wanted to keep the signal-noise ratio the same for that detector. So this particular section will just go through and talk about what the considerations they had to look at to make sure they could still maintain that with a smaller pixel. You have less photons falling on that sensor, but to make sure you can still maintain the signal-noise ratio that they needed. So let me just recommend that you go through and read that section for next time. All right, so that should take us to the end of chapter 6. So make sure you're all read up through that point. And what I want to do next week is start to talk about atmospheric calibration and atmospheric correction. Okay, so we're pretty much done now with the different kind of sensors that they are, and the radiometric considerations, and the calibration considerations, and those sorts of things. We're going to put that behind us at this point, and now we're going to take these sensors to start to look at the ground and do remote sensing. So we'll start to talk next week about different calibration methods for visible sensors and thermal infrared sensors. So we'll go through a boatload of different ways that folks do that. All right, that'll be, I think that's chapter 7. I think we're going right on here. So any questions?
So when Schott was teaching the class, the students had to be able to draw like all the different types of systems down to details, like wide scanner stuff. Same for us.
Yeah, I'd say anything in the text is something you should do. You should be able to just do a nominal design, right? If I said,
Like a push button.
yeah, what does a push broom sensor look like? What does a scanning system look like? Draw a whisk broom with a scan line corrector, something similar to Landsat. I mean, I don't expect you to know the optical designs of any particular sensor, But, you know, as general classes, yeah, that would be something very nice.
Okay.